Okay, integrating functions that we couldn't integrate nicely. If you were to split this integral up, you would have cosine x over x minus 1 over x, and you can integrate 1 over x, but cosine x over x doesn't work so nicely. So we're going to try to use Taylor's series to do this. When we do Taylor's series, here are a couple things that are nice. Taylor's series don't like division. As you can see, it's a lot harder, so let's rewrite this. This is equal to the integral 1 over x times cosine of x minus 1 dx. That's going to make our life a little easier. Now, we still couldn't split apart the integral. We would have to distribute again and get the exact same issue. But what we want to recognize is if I'm giving you this question, or Dr. G in your class, I guess these are being shared with hers as well. If we are giving you one of these questions, then we're giving it for a reason, and we want to make sure you know about the Taylor series for cosine. So it'll hopefully have some convenient factor going on. So I'm going to write out the first few terms for cosine. So this is the integral 1 over x times. Now, if you remember cosine of x, it's a series. It is alternating. Both of the trig functions are. And cosine is an even function, so it's x to the 2n over 2n factorial from n equals 0 to infinity. So all I'm going to make sure is that I alternate starting with positive. I've got even powers and even factorials. So cosine x becomes 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus and so on. You can see that, yes, it might be hard to plug in repeatedly, but if you establish a pattern, it's really not that hard. Minus 1 dx. Now, if you look inside the brackets, you've got a plus 1 and a minus 1. So those can cancel. If you cancel them, then you get the integral 1 over x times negative x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. This is exactly cosine where I start one term later in the series, so you leave off the n equals 0. So that's the only difference. To multiply through, you're just going to divide every term in here by x. So there are a couple ways to do it. We're going to say this is the integral negative x1 over 2 factorial plus x3 over 4 factorial minus x to the 6th over 6 factorial, x to the 5 over 6 factorial, excuse me, and so on. Now we still have to integrate. And integrating this infinite list is hard. So I'd rather rewrite this as a series. Okay? So I can try to figure it out from the pattern, or I can use exactly what I said above. And I'm going to do that up here. I find this easier. This is the integral of 1 over x times the series. We said that this was cosine, negative 1 to the n, x to the 2n over 2n factorial from n equals 0 to infinity. Remember, these parentheses around the 2n are important. Very different things. But now we're not starting at 0, we're starting at 1, because all we did was cancel out the first term, so we don't need it anymore. So I've now fixed the problem. We're no longer dealing with this cosine over x, because you've got 1 over x times a series, dx. Should keep that on there. This is the integral of the series, negative 1 to the n, x to the 2n minus 1, because you just divide all of those terms by 1x, over 2n factorial, from n equals 1 to infinity. We could rewrite it to start with n equals 0, but that's not very helpful. Now, I'm trying to integrate. So, to take the antiderivative of this, one nice fact is that the integral and the series swap places. That's the fact we've used a couple of times, but I'd like to write it out once specifically, once explicitly you might say. Negative 1 to the n, x to the 2n minus 1 over 2n factorial dx. When you integrate the negative 1 term and the 2n factorial term are both constants. They have no x's in them, so when you integrate with respect to x, they stay alone. When we take the indefinite integral, we're going to get a c, a constant of integration, plus the series. When you integrate, the negative 1 to the n stays alone, your 2n factorial stays alone, your x gains the power. 2n minus 1 plus 1 is just 2n. And you divide by that new power, 2n. So that's the whole difference. We've now integrated. It's still from n equals 1 to infinity. If it was from n equals 0 to infinity, we're leaving in a term that didn't exist, and it didn't make it work very nicely. So this is exactly the antiderivative of cosine x minus 1 over x. We like writing series, the sum cn x to the n without any pluses in front, but it's an unknown plus, so we can't bring it in because we don't know how it factors in. In fact, it could factor in any number of ways. So we're kind of stuck there.